Hey guys, welcome to this video reviewing Newton's first and second laws. In this video, I'm not going to go super in depth into how we derive these, but I'm going to take a look at just making sure that we understand them and we're not just regurgitating a definition. And for that very reason, jumping right into Newton's first law, I've written it out in a slightly different way than most people usually memorize it. And what I've written here is that Newton's first law says, an object will not spontaneously change its motion, and by motion we mean speed and direction, without an unbalanced interaction with something else. So let's try to break that apart and convert some of the language. The key phrases here, change motion, that's an important thing, and then also unbalanced interaction. So a change in motion, a synonym that we could use for that phrase is accelerate. And a synonym for the phrase or this term unbalanced interaction might be unbalanced force or unchallenged force. So another way we might say this statement is an object will not spontaneously accelerate without an unbalanced force exerted on it. Okay, so I have a fet.colorado.edu simulation up here. These are awesome. I have a link in the description below so you can check those out. And I'm just going to kind of demonstrate this idea. And so first what we need to do is have this guy push this box and get it moving, and I'll just leave it. And we can see that there's no friction in this case. The speed's 22.1 meters per second, and it's never going to change. So there's not going to be any kind of spontaneous change in motion here unless there is an unbalanced force interaction. So I'm going to try to make an unbalanced force here. I'm going to try to push against it this way. And notice it's unbalanced because nothing's pushing it to the right. So this unbalanced interaction caused a change in its speed. And we saw that happen. The speed changed from being 20-some meters per second now to 6.9. Now, if I was able to put another little figurine over here pushing in the opposite direction with the exact same force, what we would see is that it would be considered a balanced force, and therefore the object's motion would not change. Another key phrase here is spontaneous, so it's not going to happen without anything being done. So here's another example that we kind of skimmed over when I first started the simulation, is that the object will not spontaneously change its motion. Well, right now its motion is 0. It's at rest. So it's not going to be moving from rest unless there's an unbalanced interaction. So in order to get it moving, I might push and then let it go. And now there's no unbalanced force acting on this thing, and so it will continue to move in the same speed and in the same direction. So when we talk about Newton's first law, we oftentimes hear it said that an object at rest will remain at rest unless acted on by an unbalanced force, or an object in motion will stay in motion unless acted on by an unbalanced force. That's the same thing as what this says. So the object will not spontaneously change its motion, whether it starts at rest or some specific speed, unless there's an unbalanced interaction with something else. If there's a balanced interaction, speed's not going to change. Motion's not going to change, so it will not accelerate. This is sometimes known as the law of inertia, and inertia is a measure of the resistance to change, and so we would say that an object will not spontaneously change its motion. You would have to have some sort of an interaction for that to occur. So that's Newton's first law in a nutshell. Let's take a look at Newton's second law. Newton's second law says that the change in an object's motion, also known as acceleration as we just saw, is directly proportional to the force of the interaction it experiences and inversely proportional to its mass, or F equals m times a. Alright, now I like to rather write F net, or the net force equals m times a, because there's usually more than one force, but same idea here. So basically what this law is saying is that if there is an unbalanced interaction, known as this force over here, and remember this is going to be unbalanced, then that's going to cause an acceleration. And that acceleration is going to be directly proportional to what the force is. Basically, the way I like to think of this one in very everyday terms is if you push harder, the thing accelerates more. So the harder I push, the more unbalanced force I have, the more acceleration I have. They're directly proportional. So let's say I was going to make a graph to show the relationship between how hard I push force and what the acceleration is that I experience. Okay, so if I look at my example here, so right now the object's at rest. If I start to push it, let's put some values up here. If I push harder, we see that the speed changes more than if I push less hard. Well, now the speed barely changed at all. But if I push harder, if I apply a greater force, I will see a greater speed. And I should probably put some values on there. So what we can see then is that if I was to collect some actual data points here, I would get a direct proportion for my slope that shows F is directly proportional to A. Now, let's say I keep the same amount of push, but I rather want to see how does an acceleration get affected by the mass of the object. And I think we all have experience with this. If you try to push something heavier, it is more difficult. Okay, so let's see. If I push this box, let's go ahead and put the masses on here. So this box is 50 kilograms, and I'm going to push it with, let's go with 500. Okay. So it got up to 16.6. I don't know how long I pushed it for, so that's a little bit of a bad experimental procedure, but let's try something else. I'm going to put a 200 kilogram fridge on top of this. So now I've got much more mass, and I want to see what the acceleration is if I push with the same force of 500 newtons. So I pushed for about the same amount of time, and you can see clearly it did not accelerate as much. So its velocity did not change by as much, even though I pushed with the same amount of force. And so what we see is that the more mass there is, if you keep the same amount of push, the less acceleration you'll have. And this is actually an inverse relationship that looks like this. Now, Newton's second law basically tells us that you can always make this relationship if things are unbalanced. So you can have any number of forces that make up this total unbalanced force, and you can use the mass and the acceleration to determine what that will be. At the same time, if you had balanced forces, then you would have no acceleration. So Newton's second law can also be changed into sort of the first law, if you will, because if you say that the net force is balanced, then I'll have no acceleration and therefore no net force. This could be like an example like this, where we have a tug of war, where maybe I'm going to put two people on the tug of war and I'm going to have them pull. Well, they're pulling with exactly the same amount of force. So if I put these values up here, we see they're both pulling with 100 newtons. So the net force is going to add up to 0, and therefore there's no acceleration. But let's say that I increased this side. Well, now we see that this side is 250, that's only 100, so I have a net force of 150 in the rightward direction. But we'll get into calculations and those sorts of things later on. The idea for right now is just to know that the more force you exert, the more acceleration you have. Another way to say that, the more force I exert, the more change in my motion, or the more mass I have less acceleration unless I increase the amount of force. So direct proportion between force and acceleration, inverse proportion between mass and acceleration. So I hope that helps review Newton's first and second laws. We will get into Newton's second law in a great amount of detail and actually use it to solve a variety of different kinds of problems.